Hi, thanks for coming today. It's much time. So today I'd like to present you a bit of a research project I worked on for a few months recently. So today I'm going to present you a bit the subject. So what is Themida, what is commutation? Then I'll dig into the reverse engineering part of the research. And then I'll talk a bit about how I approach the obfuscation part of the process, and I'll show you a bit of the result I got. So first, a bit about me. So I'm Erwan. I'm currently working as a security researcher at Ubisoft in the game security team. I've got a few subjects of interest, one of which is software obfuscation, as you might have guessed. I'm active on Twitter and Mastodon, so if you want to get in touch, you can find a link. So disclaimer, it's a personal research project, and it's not meant to be. So let's start. So what is Themida? So for those who don't know, Themida is a commercial software protector developed by Orange Technologies. It works in a binary to binary way, so you give it compiled executables and protects them directly. Themida currently supports x86 and .NET Windows executables only, so XEs and DLLs. The research mainly focused on the x86 part. So for the code mutation, Themida actually relies on an engine, which is called a secure engine, to do the work. And what's nice about it is that it's actually shared by all of Orange's products, so Themida code virtualizer and license. So this means what I'm going to present today applies to all three, not only Themida. So a bit about what I call mutation-based code obfuscation in this talk. So usually in commercial protectors software such as Themida, this means that it's going to obfuscate the code without using virtual machines or interpreters to make the code more complex to understand. And it usually provides a lighter obfuscation scheme than virtualization-based code obfuscation. The nice side effect of that usually is that you get a lower performance impact, so it's nice if you want to obfuscate functions that are performance sensitive. It works by adding or modifying the original machine code while preserving the original behavior of the code. And it can sometimes modify the original control flow graph, but it's not always the case. So now, what was the initial motivation of this research project? Well, it was basically just to see if it was feasible to automate the deobfuscation of code mutated by Themida, basically. And for that, I had a simple plan, which was first trying to understand thoroughly how Themida's mutation engine worked, what were these features, and then hopefully try to find weaknesses that I could leverage to make the deobfuscation part easier. So what I mean by weakness is an invariant or invariants that I could rely on, that the invariance in the way the mutation engine mutates the code, that I could leverage to take shortcuts during the deobfuscation process, basically. So to start the research, I first wanted to get my hand on a version of Themida. So fortunately, a demo version of Themida is freely available on Orange's website. An important thing to note is that this demo version contains the same mutation engine as the paid version, so it's pretty nice. I checked that by comparing with in the white samples I had from previous researches. And the idea was to use this demo version as a black box that I could give input to and see and observe the output and try to understand what's going on. So a quick look at what the mutation looks like if you don't know. So basically, if you give Themida the function on the left, give a CFG containing 6 basic blocks, it will give you something like what's on the right, which is a bit unreadable, with now 74 basic blocks, so many more. And it's the same for the actual machine code. Your original code, who was 71 instructions long, is now mutated into something that's 2,000 instructions long, and it's pretty unreadable, and you don't want to deobfuscate that by hand, basically. So this is what they're trying to automate this task. So the initial approach was, as I say, a black box approach. So I wanted to be able to give Themida very precise inputs, so machine code input, that I could then transform using Themida into a mutated version, and then compare the two, compare the inputs and the outputs, and try to reverse engineer the mutation engine this way. So for that, I needed to generate the machine code in a precise way, an exhaustive way if possible. So for that, I found a very nice project which is called uops.info. And this project provides a big XML database that contains descriptions of many, if not all, x86 instructions. And it also provides a script that you can use to generate assembly code for those instructions. So this allowed me to generate the file that you see on the right, which contains thousands and thousands of x86 instructions, basically, which I separated into their own dedicated functions. This is just a more practical way to work with Themida, so that they could analyze, okay, how the end instruction is mutated, how the add instruction is mutated, etc. So in the end, it gave me this input generation pipeline. So one branch is coming from the uops.info part that I just showed you, which I could then assemble into machine code. Then I also had a few manually coded C functions that I used to test other features of the engine, such as the control for graph modification, for example. So this was pretty nice in theory. And then when I tried to give that to Themida, the first thing that happened was that it crashed when trying to obfuscate the code. So it seems that some instructions are not properly handled by the mutation engine and it makes it crash. So fortunately, not a lot of instructions reproduce that behavior, but I had to basically not try to obfuscate those instructions to be able to continue. So software have bugs. And more bugs, potentially. So this one was a little bit more annoying, because then the crash was gone, but I started entering infinite loops when trying to obfuscate the code. So this was annoying because it was not deterministic, so randomly one macro, then the other was making the engine enter infinite loops. And so I had to restart Themida every time to be able to restart the control process, and each time disable the faulty macro. So it took a little bit of time to be able to generate an actual binary that was projected. But then we was able to finally generate such a binary and start the analysis. And I'm going to present the features that I could identify thanks to that. So I mainly identified 3 obfuscation features / classes. So the first one is what I called opaque code entry. And the second one is junk code assertion, which is a common obfuscation pass. And the third one is the instruction substitution feature, which has a few variants, and I will describe them one by one. So the first one, the opaque code entry, what it does basically is that when you obfuscate a function, Themida is going to redirect the code to its own modified code. But first, it's going to redirect the code to a trampoline, which will compute dynamically the address of the mutated code. So this looks like that. So you've got your function that's been obfuscated. So now it's just a jump, which jumps to a trampoline, which looks like that. So it's not obvious at the beginning what this piece of code does from the CFG. We see a loop and conditional branches. But actually, if you try to understand what's going on, you'll see that only the red part here is actually doing meaningful computations. And this is the part which computes the real code's address. So this is a bit annoying when you deal with static analysis because it hides the real code location. So the second part is the Gencode insertion. So from what I could find out, this path is triggered randomly, but for 75% of all instructions in the end. So this path just inserts useless code, Gencode, before or after original instructions, or both. And the good thing to note is that the Gencode is inserted in such a way that it cancels itself out within a single basic block. So I'll explain a bit after what I mean by that, but it's going to be useful for us. Quick look at what is Gencode if you're not familiar with the concept. So for example, if you've got your original instruction in yellow, move EVX, CCX, you can insert some piece of code that will do computations, but that do no real work in the end. So in this case, for example, we push EAX and we pop EAX at the end, so restoring the original value of EAX, and we can do useless computation in between to make the code more hard to read, basically. So that's one thing Themida does. And the final, most painful feature to analyze is the instruction substitution path. So from what I could find by comparing a lot of inputs and outputs is that the mutation engine is capable of substituting 14 instruction classes. These are the ones. So it's able to understand the semantics of the instructions and replace them with completely different instructions that do the same computation, basically. This path is always applied when a supported instruction is encountered. So, quick example of what this looks like. So, for example, if you give Themida the exchange instruction on the left, it's going to output the XOR pattern that you see on the right. So, this pattern is a known pattern that performs an exchange between two variables without introducing a temporary variable. So that's one way Themida mutates. And another example is this one. So for example, if you give Themida the move RDX instruction on the left, it's going to input something like what's on the right. And what it does basically is remove the constants from the code and replace it with a dynamic computation to hide the original constant value. So pretty annoying to deal with in practice. Quick word on the flag register, because this is an important piece to understand when doing obfuscation and deobfuscation. So the flag register is not really considered by Themida in its obfuscation passes, so it does not preserve the flag register. So Themida, to preserve the original behavior of a piece of code that uses conditional instruction, basically disable the obfuscation passes completely for certain instructions that are using the flag register, basically. So this looks like something like on the slide. So between the add and the section instruction, every pass is basically not mutated. So these were the features. During the research, I also encountered a few bugs in the mutation engine on top of the two previous ones. So one of the bugs is this one. So you give the mutation engine some instruction, and the output might be something like what's on the right, which is garbage code, basically. So if you try to execute this code, this will crash. So this means that sometimes the mutation engine might break your code without you knowing. So pretty annoying. So it's a reminder when you obfuscate code, I encourage you to test your obfuscate code afterwards to make sure it works properly. And the second kind of bug, which is even more annoying, what's this one? So there's some instruction that the mutation engine will mutate correctly, at least in a correct machine code, but the resulting machine code does not perform the same operation as the original one. So for example, in this case, you give extend DH on the left, which is a nope. And Themida is going to use this XOR pattern again blindly without realizing that XOR DH does something completely different than a nope. It actually sets the value of DH to 0. So that's pretty nefarious because that creates hard to troubleshoot bugs in your code. So keep that in mind. Alright, so these were the features and bugs, but what about the weaknesses? So from what I could find, there are three main weaknesses that are useful to deobfuscate the mutation of Themida. So the first one is the fact that each basic block is mutated, or is created from one original instruction and only one. So it seems like the mutation engine starts by splitting the basic blocks into one basic block for each instruction, and then it applies the mutation passes on each of these basic blocks separately, so on one instruction at a time. So those two weaknesses combined allow us to take some shortcuts during the deobfuscation. I'll show you in a bit. And finally, the third weakness, which is interesting for us, is the fact that the mutation engine does not really mutate the original CFG. So it will split basic blocks and introduce conditional jumps, but it will not modify the existing conditional branches. So we do not need to reconstruct the CFG page. So this is pretty nice. So we know a bit more about the mutation engine and its weaknesses, but how can we go about simplifying the code now? So at first I thought a bit about using maybe code optimization solutions. So for example, lifting the machine code to LLVMIR, and then reusing LLVM optimization pipelines to automatically deobfuscate the code with the optimization passes. So this was alright, but felt a bit overkill in my case. And I felt like working at the basic block level directly was a more efficient way to deobfuscate the mutated code, basically. So this is why I finally went the program synthesis way, at least a simple form of program synthesis. And for that I use symbolic execution. So I'll show you a bit how this works. So the idea for the deobfuscation process was this. So first, we need to, when you see a obfuscated function, you need to figure out where the mutated code actually is. So you need to reverse the trampoline. And then once you know the code location, you need to start simplifying the code, so each basic block in our case. And then finally, we want to maybe reassemble the simplified code and be able to relocate it somewhere in the binary. So in this talk, I'll only present the two first steps, which are the most important ones. So the first step, defining trampolines. So we've seen what a trampoline looks like, and we can use one weakness of trampolines to facilitate our work, which is that the trampoline's logic is always the same. The exact same logic is shared between all trampolines of all the functions that you're going to mutate. So this means that we can basically assume that trampolines are always going to look like that, like this CFG. And so we can start simply symbolically executing at the start of the trampoline. And then we reach the first conditional branch, which we know must always go on the right branch. Then we reach the second conditional branch, which we know must always redirect to the left branch. And finally, we reached the end of the trampoline, and we actually executed the last part of the code, which is actually the part of the code that computes the mutated code address. And so we can then extract this address directly from the stack, symbolic stack. So this is pretty nice because it works pretty well and allows us to defeat the trampolines. Now this leads us to the second part, which is, okay, we got the code location, but now we need to process it and simplify it. So for that, we're going to work at the basic block level, so iterating over each basic block. And we have mainly three cases that we need to deal with during the instruction synthesis. So the first case is the simplest one. It's the case where the mutation engine did not insert any junk code and also didn't substitute the original instruction because it's not one of the 14 instruction classes that the mutation engine can substitute. So this gives us this kind of basic blocks where basically the original instruction is alone and we can just keep it like it's not even mutated. So we have nothing to do basically. So this is nice. But then there's the second case, which is a bit more painful to deal with. So this is the case where junk code has been inserted, but the original instruction is still in the basic block. So you can see in red, this is the original instruction in GPS, which has not been substituted. So here we can avoid synthesizing instructions ourselves by just using the fact that the original instruction is supposed to behave the same way as the whole basic block, because the gen code cancels itself out within each basic block, if you remember. So what we can do is use symbolic execution to perform that like research algorithm, so to say. So we want to start by symbolically executing the basic block. So this is what you see on the top, the result of the symbolic execution for a block. And it looks bad, but we need to remember that we don't need to care about the flag register because Themida does not preserve those when they are not needed. So we don't need to deal with them. And if we do that, we are left with actually the core of what's the basic block semantics. And here we can see that it basically moves XMM0 into the memory location at RDI plus 0 XMM. So, right. So now what we can do is execute each instruction symbolically in the basic block independently and try to see if one instruction does the same operation basically. And if we do that, we can find that what you see at the bottom is the symbolic state at the end of the execution of move UPS, which was the original instruction. And we have basically the same expression as the basic block. So if the two are equal, we know that we have found the original instruction, the basic block, and we can only keep that one, and we know it's the original one. So that's pretty cool because we avoid having to basically synthesize all the x86 instruction set. And finally, there is the third case, which is where the actual synthesis, which is a glorified pattern matching really. And we have to do this for the 14 instruction classes, which the mutation engine is able to substitute. Because basically, in this case, we have no choice but to try to understand what's the original instruction, because it's been replaced with another sequence of instructions that we cannot find. So in practice, this looks a bit like the case before. We want to first execute the basic block symbolically. It gives us something like that. So we must also remove the things related to the flag register. And if we do that, we're left with, again, the main, the core of the behavior of the basic block, and thus of the original instruction. And in this case, we can see that it seems to be that R9 has been moved into R13. So we could say, okay, so this looks like it's a move R13 R9, right? So this looks pretty straightforward. And actually, we can do this for all of the 14 instruction classes with not so much code. You have to trust me on that, but basically this is what I did. So I implemented a basic pattern matching algorithm over the symbolic states of the basic blocks, and try to say, okay, this looks like a move, so emit a move. This looks like an add, so emit an add. This looks like a sub, etc. And do that for all the 14 instruction classes. So if we do that, we can manage to make something that works pretty well. So this is the result of what I developed. So it's basically a Python program, which uses Myasm as a symbolic execution engine. And basically you give it a protected executable and a list of addresses, virtual addresses, which are the addresses of the function that have been mutated. And it will do what I described before automatically. So first resolving the trampolines, and then deobfuscating each basic block one by one, and then re-emitting machine code, simplified machine code, and then rebuilding a binary file that you can even execute. And that should behave the same way as the original, but with simplified machine code. So it works pretty well in practice. I've done many test cases, and I also had the opportunity to test on real-life samples, and it worked very well. So pretty happy about it. So in the code, if you want more precise results, so the CFG recovery is pretty good because, well, since no CFG modification is made by the mutation engine, we can basically recover it perfectly. There's just a little jump at the beginning, which adds one basic block, but that's it. And as far as the machine code is concerned, we can get pretty close to the original. So the original one was 71 instructions long, the deobfuscated version is 74 instructions long, and it's pretty close to the original instruction. There are some differences, but the semantics is the same. So we won't need to worry about that. Some instructions are a bit different, but the behavior is the same. So that's pretty nice. So before concluding, I'll do a quick recap. So a few weaknesses really facilitated the work for us. These are not weaknesses that are very hard to address by ORMs, I think. So they may be able to fix this fairly easily. But those weaknesses allowed us to use static symbolic execution in a very effective way, which is not always possible, and in a way that scales fairly well. And because we only work at the basic block level with symbolic execution, we avoid classical path explosion problems, for example, so it works pretty well. And in the end, we're able to recover very close to machine code, very close to original machine code, which is not always the case when dealing with deobfuscation. So it's pretty nice. And finally, we can even regenerate working binaries that run on our deobfuscated code, and we can then even use Express decompiler or binary ninja this decompiler to get a clear view of what the mutated code was doing. So that's about it. So many details weren't possible to put in the slide, but I think I will publish a web series about it pretty soon. So if you're interested in that, stay tuned. And that's basically it for me. So the code is available on GitHub, so you can try it, see if it works out for you, and open issues if you find any bug. There's also a binary ninja plugin for that, so you can interactively run the deobfuscation on certain addresses, and it patches the binary directly for you. So it's pretty nice. So yeah, that's it for me. I'd like to thank my friends Jesse and Maxime for helping me review the talk and making it better. So that's it. I'll answer the question. Yeah. Go ahead.
Have you studied the evolution of the Packer over time and locate how much extra work do you think would be needed if some changes would be made to the Packer?
All right. Sorry, the question was, did I look at how the mutation engine evolved over time, and is it can I predict whether it will be difficult to follow with the updates or not? So in this research, I worked only on Themida version 3, and it seems like there has not been any substantial updates to the mutation engine from the first 3.0 release up until now the 3.1.9, if I'm not wrong. And so not many updates so far as I can tell, because as you may have seen, the demo version I used was 3.1.3, which is a bit outdated, but from what I could find out, it's still Well, the deobfuscation worked the same way on more recent version of Themida. Now about the updates. So if it's very simple, I'd say updates about introducing a new kind of substitution, for example, substituting a new instruction. This should be fairly quickly to follow because the pattern matching is already in place. We just need to add a new case and deal with it. And so that should be fairly doable. But I think the most risky kind of update, I think, would be to, if Orions really modify the way the mutation engine works. So for example, merging basic blocks after mutating them would basically make it very hard to figure out, okay, so I need to start here and here the symbolic execution, and I know that it's gonna have the semantics I'm looking for. So if they do that, this will probably break the current deobfuscation algorithm in a very hard to fix way. So, yeah.
I don't have a question, I just have a comment.
Mm-hmm.
Exactly what you said, they're already doing in a new version of Themida.
Yeah, okay. That's interesting. And I think also, not look at it too thoroughly, but I think in their via enter routines, they seem to do code mutation in a very similar way to this mutation engine, but where they merge the basic blocks already. Not 100% sure about that, but yeah, that's something they can really easily do, I think. So probably already done even. So okay. Yeah. So the thing is that thanks to the way the mutation engine works, there are a few cases that are hard to get properly, especially on push and pop, because there's junk code that might interfere with what you see. So you have to be very careful about that. So there were a few false positives I dealt with manually, but thankfully there were not a lot of them, because mostly the false positive, there are not a lot of instruction classes that are mutated, so it limits the false positive for that case. And for other cases, it's more about flags register that could really make it hard to pattern match, but the fact that the mutation engine disable completely the mutations when flags register are used, then I basically have to, I can avoid the issue completely. So if it was more complicated to deal with flags register, that would create a lot of false positives, I think, with the current approach. All right, so I think we can end it here, and I'll give the mic to the next speaker.
Thanks.